We are going to start factoring polynomials, which is part of the way that we use to solve polynomial equations. To this video, we're going to talk about factoring using patterns. We're actually going to take two swings at factoring. The first one is patterns. These are the ones where it just kind of works out for us in one of these 5-6 ways. If it doesn't work out one of these 5 or 6 ways, we're stuck with what we call synthetic division. We're going to break down our polynomials using synthetic division, which is something that's going to come up later. So for right now, there's just a few specific patterns that we want to watch out for. And this is sort of when you first encounter a polynomial, look for these patterns, because once you learn to recognize them, it can reduce your workload. But if none of these things work, we do have something to fall back on. We just haven't learned it yet. So the first thing you should always look for is a greatest common factor. That frequently is a number, but it can also have a variable in it. So if you see the same number or factor or the same variable factor in all the terms, we're going to factor that out first. A lot of times that'll take care of things right away. If your polynomial is a binomial, if it has only two terms left after that, then the two patterns to look for are difference of two squares and sum of difference of two cubes, for which I have the formulas down here. If what is left over is a trinomial, we're going to look to see if it's a perfect square. The pattern for that is on the bottom here. And then we're also going to check for something called quadratic form, which I'll cover when we get back there. We will then talk about factoring by grouping, which will work for any polynomial with an even number of terms. Usually you'll see 4 or 6 in Algebra 2. We don't get ones that are bigger than that usually, although it's theoretically possible. And then at the very end, I'll do one example where we actually solve an equation. The basic process is you factor and then set each factor equal to 0. So you use all 4 of these patterns when you're solving equations. It's just a matter of once you get it factored, what do you do with the factors in order to kind of finalize. So I'm going to get into the examples. I talked through these by name, but really the best way to experience them is to see the examples. So my example for number 1 is 3x cubed plus 6x squared minus 45x. So this is a cubic function. We're looking for at most then 3 factors. Well, we should have 3 linear factors, although we'll find out we can't always factor completely. Anyway, 3 is the big number here. So I'm looking through 3, 6, and negative 45 are all multiples of 3. And all these terms have at least x to the first in them. This one only has x to the first, so we can't factor out more than x to the first without creating fractions anyway. When I divide 3x cubed by 3x, I will get just x squared. If I pull 3 out of here, it leaves behind a 2 and an x. And when I divide this by 3x, the x's cancel, and I've got only 15 left. Now I've partially factored. I have my monomial factor out front, and I have a trinomial here. I could look for these patterns, except since this is just squared, this is something that we factored several times when we did quadratics. So this is just a trinomial. We're going to factor into its 2 pieces. 2 numbers that multiply to negative 15 and add to positive 2 are going to be positive 5 and negative 3. Multiply to 15, add to 2. So positive 5, negative 3. And now I have 3 linear factors, which is what I predicted, and it's what I've got. So I'm good to go. Number 2, we're going to look, or 2a I should say, example 2a, difference of 2 squares. This is also something that should be familiar to you from earlier this year. If you see 2 pieces, and one of them is a square, 4x squared is a square, and 49 is a square, and they're being subtracted, that's a difference of 2 squares. So take a minute and think about what they were before they got squared. That's a step I usually do in my head, but 4x squared you get from squaring 2x, and 9 you get from squaring 7. So the pattern is you use them, the square roots here. You do one with plus and one with minus, and then you call yourself done. So there it is. Now the sum and difference of cubes is new to you probably. 8x cubed plus 27. Now the cubes can be either a sum of two cubes or a difference of two cubes, and either way you can factor it. The only thing that changes between these two is the pattern of pluses and minuses. The first sign is always the same as what you started with. The second one is always opposite. The third one's always positive. This is actually b squared, so even if this were negative, b were negative, when you squared it, you'd get positive. Same thing with the a squared here. It's actually positive. But so in this case, because, well, actually, I'm getting ahead of myself now. So 8 is a cube. That's 2 cubed. And x cubed is a cube. So this is 2x cubed. And 27 is 3 cubed. So the first thing I do is identify a. So a cubed is 8x cubed, which means a is 2x. B cubed is 27, which means b has to be 3, because 3 cubed is 27. Then I just follow the pattern through. Oh, except I want this one. Started with plus, so I need a plus b. And I just said a was 2x, so start there, plus b. b is 3. And then in the next one I need a squared, so 2x squared, which is 4x. Sorry, 2x all squared is 4 times x squared. And then minus a times b is 2x times 3, which is 6x. And then b squared would be 9. And there it is. This trinomial, you will not be able to factor this trinomial. Don't try. So this is a linear factor and an irreducible quadratic factor, which is it's something that happens in algebra. So this we started with a cubic, so we have one linear factor. The quadratic is squared. It counts as 2. That's a total of 3. We're good to go. My number 3A example. Perfect square. This is a pattern that really you could get all the way through pre-calculus and never actually learn this pattern, because you can factor this using the same techniques we used at the end of example 1 here, where you're looking for the numbers that multiply out correctly and you just guess and check. But if you're trying to figure out all the different possible combinations that multiply to 64, you're going to get frustrated very quickly. Whereas recognizing this is 8x squared, and this is 3 squared, and then being able to check the middle to make sure it fits the pattern is much less work than trying to figure out how to split 64 up. I mean, you could recognize it's a square and just always try that first. You could always just try the square roots first, and if it works, you're good to go. But the pattern we're looking for is the middle should be 2 times a times b. That is before you square them. So 8x times 3 is 24x times 2 is 48. So this matches the pattern. So if you recognize the pattern and you check to make sure the outers and inners are twice the product of a and b, then you can just go right to the square. Although if you want to do it by making your 2 parentheses and putting 8x plus 3 times 8x plus 3, like, you can get by without ever learning this one. It's a little faster. 3b, quadratic form. Now, quadratic form I think it's an interesting idea. Whoever thought of it first certainly earned their pay that day. So the idea is, if we have a trinomial, even if it's not actually quadratic, we can factor it using the same strategies that we use for quadratics. In this case, though, we have a greatest common factor. Hopefully you notice they all have m. In fact, they all have at least m squared. So I'm going to factor out an m squared. These are all also multiples of 3. It's a popular choice because it's not 2, but it's also not too big. So when I pull out the 3, that leaves 1 and m to the 10th power. 54 divided by 3 is 18. M to the, see, I pull out 2, so there's 5 left. And then 51 divided by 3 will be 17. Both m's are gone. So when you have a situation where the front term has a power bigger than 2, but as long as it's twice as big as the one in the middle, you're in what we call quadratic form. You can treat this like a quadratic and use those same strategies. So in order to get to m to the 10th, we need m to the 5th times m to the 5th, which is how our outers and inners are going to add up to something with m to the 5th in it. The two numbers I need here I have to multiply to 17 and add to 18, which makes them 17 and 1. So looking through, this is factored. I mean, it looks quadratic, but this is really m times m. This is two linear factors. I've got, this is 5th degree and this is 5th degree, so I still add up to 12. It's all good. But I don't have a pattern for sum of 5th powers. I don't have that pattern. By binomials, I look for a greatest common factor. I look for sum or difference of cubes and the difference of two squares. I don't have any of those. So for now, I'm going to just kind of park this here. You can solve these by, well, I'm about to get there anyway. So I can actually find zeros for these if I'm willing to use 5th roots. M to the 5th equals negative 17. So m equals the 5th root of negative 17. There's the 5th roots of negative 17. There's one real one and there's like 4 imaginary ones. That's well beyond what we're going to do. When you get a situation that's a binomial that's not a sum or difference of cubes and has no common factor, you're done factoring. Solving equations is kind of another thing, but in Algebra 2, we're not going to do that to you in a situation where you're solving the equation. So we're definitely done factoring at any rate. Number 4. Usually we like to get down to linear factors, but it doesn't always work out the way we would like. So my example number 4, factor by grouping. This one is also a trick. So like once you kind of see the trick, it might make sense, but it's not something that would have occurred to me until somebody showed me. So the way factor by grouping works is we assume that there's a common factor in here somewhere. It's just we don't know what it is. Although the factor we're looking for is not a monomial. It's not like we did up here where it's 3. It's a binomial that we assume is a sort of a factor in here. And we're going to try to find it. And so what we do is we split it into 2 halves. We take the front two, 27t cubed plus 45t squared. And we take the back two, negative 3t minus 5. And we analyze them separately. And we're looking for a greatest common factor in the front and a greatest common factor in the back. Here in the front, 27 and 45 are both multiples of 9. And they all have at least t squared. So 27 times 3, sorry, 9 times 3 is 27, and t squared times t is t cubed. And 9 times 5, I don't need any more t's. So I've got 9t squared times 3t plus 5. That's this piece here. I come over here, and really what I'm hoping is that this will end up the same as this. I see it's pretty close, but there's a common factor of negative 1 here, which if these are negative when you're factored by grouping, go ahead and factor out the negative. Really, if the front one's negative, I recommend you factor that out. So looking through then, if I pull out the negative 1, this is 3t plus 5. Now, factor by grouping is a gamble. If when you do factor by grouping, these two turn out to be the same, which they did in this case, it worked, and you're good to go. If these are not the same, you got to bail. You can't factor by grouping if these don't turn out the same. So pull this one out front. 3t plus 5 is your common factor here. It's your factor. So you pull it out front, and then what that leaves behind are the ones that got factored out earlier, 9t minus 1. So this is the common factor. You're going to factor it out front of the larger problem and leave behind the 9t minus 1. That's factor by grouping. Now we're not quite done here. This one's linear, but this is a difference of 2 squares. So this is 3t minus 1 and 3t plus 1. And now we have 3 linear factors, which is much happier. So that's factor by grouping in a nutshell. The last example I have, I'm going to solve an equation just to show you that last step. 2x to the 5th equals 12x cubed minus 16x. Now the whole point of factoring is to produce a string of numbers that have to multiply to 0. So we really need one side to be 0 if we're going to factor, or if we're going to factor to any good use. So I need to pull everything over to one side. I've said before, and I'll say it again, I always go to the side that's going to make my leading coefficient positive. So I'm going to stay on the left here where my 2x to the 5th is, which means I need to subtract 12x cubed and I need to add 16x. Then I'm going to look for a greatest common factor. Everything here has a 2 and at least one x. So that's x to the 4th minus 12x squared plus, no, 6x squared plus 8. Okay, so this is not a quadratic, but it is in quadratic form. Half of 4 is 2. So we're going to factor it like a quadratic, but these are going to be x squareds instead of just x's. To multiply to positive 8 and add to negative 6, I need negative 4 and negative 2. This one here is a difference of two squares, x minus 2, x plus 2. Linear factor up front. This one is not a difference of two squares. So as far as what we're doing today, we're just going to leave it. But in this case, we're trying to solve for this polynomial equation, so I'm not quite done. The point of factoring is the zero product property says if you multiply numbers together and the answer is 0, one of the numbers has to be 0. So the fact that these are all being multiplied together and equals 0, the only time that'll ever work is if one of these factors is 0. So we set them each equal to 0 separately and figure out all the different x's that will make at least one of these 0. So this one we divide by 2. 0 divided by 2 is 0. So x equals 0 is one of our factors. X minus 2, we add 2 to the other side. X equals 2. Subtract 2. Here, though, we're going to add the 2 over there. And then we got to take the square root. When you take the square root of x squared, don't forget your plus or minus. So that's part of the reason we couldn't factor this over rational numbers, is the zeros are actually square root of 2 and negative square root of 2. So you could have factored this as x minus the square root of 2 and x plus the square root of 2. It's not something that we're expecting you to do. But when you're solving this equation, you should be able to solve any quadratic factor using, at the very least, the quadratic formula, if you can't figure out the factors any other way. So we have a list then of zeros. There's a bunch. We'll have up to 5. For a 5th degree polynomial, we're expecting up to 5 zeros. And they are 0, plus or minus 2, and plus or minus the square root of 2. That's all 5. So if you remember this list, I actually put it in this order, not the same order our book has it, because this goes from basically this is the order I go in when I'm trying to do these. Look for greatest common factor always first. If you forget that, it can be a real headache later. If it's only a binomial, difference of squares and difference of cubes, or sum of cubes. If it's a trinomial, you're looking for quadratic form. That's the factoring we did like right here. If you recognize a perfect square, that's good. Technically, this one is optional. And then anything bigger than that, if it's got an even number, try factor by grouping. And then, solving equations isn't really on the list of how I factor, but it's something I wanted to mention. That should get you started. Please contact me if you have any questions.